Open Symposium dedicated to software sustainability. Just before to start, just a little announcement, logistic announcement. If you can go to the desk during the break in order to sign the paper, in order to see if you are here or not. And even if you signed yesterday, you have to re-sign today. So go to the desk at the break, please, and sign the paper. Okay, so this second day is dedicated to software sustainability. Yesterday we were talking about benchmarking, and just some word of introduction on why we decided to focus on software sustainability. So we start from the status that many software development are funded, but for very few have a long-term strategy for long-term sustainability. So we have money to develop, but not no money to sustain for a long-term the development and of the codes and of the software. And for our point of view, there are three main axes about software sustainability. The first one concerns the performance portability, since we have to develop some software, but they have to run in different architecture, and also to support the evolution of different architecture. The second one concerns long-term sustainability and how you can maintain the code, the software for a long time. And the third pillar or third axis concerns environmental sustainability, how you can design, how you can adapt your code in order to minimize the footprint on the environment. So during this second day, we try to address the three different topics and try to have some thoughts about these three main axes. So the program you have on the website, but just some short summary of how we construct the program along the three axes. So we will start with a keynote from Marta Perec, and after we have the first session about performance portability. So after the lunch we have the second session about long-term sustainability, and we will finish with environmental sustainability. And we'll have only two talks during this last session, since Simon McIntosh will not come today. Okay, so I propose to start with Marta Perec, who is the Fair Data Program leader of NWO.
Thanks so much for inviting me today. My name is Marta Perec and I'm from the Netherlands. I'm the third data. Maybe I took the wrong microphone. That was a test, huh? Failure. Thanks so much for inviting me today to speak at the conference. My name is Marta Perec and I'm coming from NWO, that's the Dutch Research Council, which has just started a new department called Open Science NL. And today I would like to tell you a little bit about Open Science. Before that, I wanted to say that in case you like the slides for today's presentation are available. I also stick it to the Google Drive. I noticed that what's available, so you can also find the presentation in there. Just a little bit about me. I'm a researcher by training. I did my PhD in biology, developmental biology, epigenomics afterwards when the big data started. And afterwards, I moved to support researchers professionally with their skills on managing research data. So I have about 10 years of experience in that at various universities and now also at the Funder. And I joined the Dutch Research Council in July this year, so I'm relatively new, I'm still learning about what they do. And I also wanted to share one disclaimer before I start. I'm not a computational scientist, so you are the experts. I probably will not understand many things that you are saying today, therefore I'm very interested to learn from you today. And I'm also not a big data expert, so please bear with me, and if I say something silly, please try to be understanding that I'm not an expert on that, but hopefully I can share something useful nonetheless. So, you know better than I do, I will not dwell on that, but you know that there are lots of challenges, lots of developments currently in science, and I think especially in those disciplines that you are working, you know, with exponential data storage needs, with ever-growing computational demands. You know better than I do. Before I started the talk, Chair was telling me about the list of, you know, the most powerful computers, you know, computational resources which are available now in the world, which is super impressive. You know better than I do. And exactly as you have introduced at the very beginning, Christophe, we need to have more sophisticated software, more complex analysis to be able to analyze, process the data that we are interested in. And the question arises, and I think that's why we are here today, is it all sustainable? You know, again, better than I do, so I'll go through it very quickly. There are huge environmental impact of computational resources that you'll be discussing this later, so I will not delve into that, you know, more than I do. But also there is this big problem about accessibility of data, especially when you are dealing with large amounts of data, of methods, the sustainability of software, the topic of today. That's quite a big issue indeed if software is not sustained, it's not available later on. What can we do with research reproducibility issues? And something that perhaps is not a topic of today, but I'm sure you have heard and experienced that yourself, bias in data, and especially bias in data, especially if we don't have access to the data. So we can't really say what kind of data sources have been used, and thus what kind of biases our analysis, our research outcomes can lead to. And furthermore, with all those problems, we also have that issue of skills. What kind of skills, what kind of capacities do we need as a community to be able to cope with all those challenges? And my hypothesis for today, something I would like to walk you through during my talk, is that open science can really help to enable sustainable research ecosystems. And maybe before we start, I would like to share with you an almost personal story, or you know, for you to understand also where I come from. That's a picture. You probably cannot find me because people change and I'm now many years older, but this is me in here when I was starting my PhD at the University of Cambridge. And this is the cohort of students who were starting together with me. And the story is almost personal. It's not personal. This will be about my colleague Tim, who was my good colleague at the time when we started together. We were at the same institute. So my colleague Tim started his PhD. His task was to build on 2 large seminal papers from the research group where he did his PhD. And you don't have to read the titles, probably they will not mean anything to you, that's fine. What I wanted to say that he was doing his PhD at the University of Cambridge, and one of the biggest, let's say most famous in the field institutes, in a very famous research group, you know, and these 2 papers in the discipline were from that so-called high impact factor. So, you know, very powerful, impactful stories. So when he started and he got to know that he had the chance to work on this project, progress on that, he of course was super excited, you know, very cool story I can build on, you know, I'm really keen as a PhD candidate to do so. But in a year later on, you know, after starting his PhD, he became more and more unsure about what he was doing. Because in biology, where I come from, the first thing you do when you want to build on somebody's findings, you try to reproduce those findings. Well, after a year of doing experiments very carefully, he was sharing this with me almost on a weekly basis. He couldn't do that, you know, and the problem was his supervisor was getting frustrated with him. Well, you know, you PhD candidate can't even reproduce the findings of that, you know, famous postdoc who by now has left the research group and set up a group in France. I hope you are, maybe you are here actually, it would be interesting to know. But the problem was that the original data unfortunately couldn't be found, even within that research group where my colleague was starting. So he was a little bit well, I don't know what am I doing differently from the other person, what's happening, how can I learn if I can't learn? The person was not available to really answer questions or so. So 2 years later, he still couldn't even reproduce the findings, which of course is a big problem. What will happen with your PhD if after 2 years you are stuck on point number 1, you can't even do what the other person did, So his supervisor was also very frustrated with him. I spoke with him, it seems like everything what you're doing makes sense. And at that stage, he started speaking with people who were managing our microscope facility at that institute. And it turned out these smart people had backup systems of everything, and through painstaking analysis and process, they were able to find all the raw data. And what happened after all this sort of investigative analysis, even instead of doing a real PhD as he wanted, he published a paper, and again, not to go into the details, you don't need to read the title. What turned out is that all the work of the postdoc before that he was trying to reproduce were false positives. So it was a technical error, misuse of the technique, false artifacts, sometimes it happens as a result of a technique used. So my colleague Tim, you can see he's the first author here, he published a paper, of course, in a lower impact factor journal because nobody cares about, the technical issues in a technology, well, whatever. So in the end, as you can probably foresee, the 2 papers, the big papers, were retracted. Great, 2013 retractions. And you might say, well, what's the story, The science self-corrected itself as it should, so what's the big issue here? And the big issue here, forgetting about the career of my colleague Tim, who really wanted to be a principal investigator to research, but at the end of the day, he had a paper nobody cared about, and he spent his PhD correcting somebody else's science. He couldn't stay in science for reasons that probably many of you are familiar. But abstracting from the personal story of my colleague, that has been 6 years from the original publication of the paper in 2007 to 2013 when the retraction happened. It's quite a lot of time, I think, for science, for us as academia, as overall. And especially when you think about is how many other people, again, I wanted to remind you, this was quite a famous research lab from Cambridge with quite impactful papers in that particular field and disciplines. How many others in the world were trying to build on those findings? What happened to all of them? What happened to their careers? What happened to their research? How much money did it cost all of us, And here, hopefully, also the issue of sustainability comes in, That's in the end primarily taxpayers' money that we are investing in research. But also, I can dive into that if you like during a break, but there is a lot of confirmation bias, especially in biology, due to the way we assess and test hypotheses. So how many other false positive reports were published, and those negative ones ended up either not published at all, or that's a technical error, we don't really care about it, And when you think about this, that's something that could have been so easily fixed if the raw data was available with that original paper, First of all, anybody in the world could have hopefully looked at the data and said, well, it's just technical error, we tried that paper earlier, Perhaps the whole course of things would have been different if that one little thing happened. And that's part of open science, what I'm talking about, sharing your research data available with the others to help science progress a bit faster. And with that, I would like to introduce you to hopefully share your own experiences, hopefully not as interesting as I have experienced myself, but I'm really curious how that works in your field, in your disciplines. So if you could go on your phones to www.menti.com and write down those numbers 7248 3545, or alternatively just scan that QR code. If you, of course, have internet, but I'm sure your crowd has internet and Wi-Fi connection sorted out. You can do it on a computer as well, of course. Meantime, I will open the slides with the quiz. So you can still see the code, you can also just take a picture of that. I can see that 30 people are joined, 33, some people are still joining. Is there anybody else who's trying to join in and it's a little bit more time? If you can raise your hand, I'm still waiting, we will wait. see the link also up, above menti.com, and the code is 72483545. We have 41 people. Shall we wait a little bit more, or are people getting in? You can see that some are still taking pictures, so let's wait 10 more seconds. Okay, let's try to move on. You can join in as we progress. That will be the same code used later on. So if you are still joining, don't stress out. I have a question for you. The first one, have you ever experienced difficulties reproducing somebody else's experiments? Some yeses. Oi, oi. I'm happy to see that there are no's as well. That's reassuring. Some people are unsure, which is fine. I'm always curious when what's the rationale behind, but I will not be putting anybody on the spot. Most people have experienced problems. It's interesting, when I was coming to speak at your workshop, I was actually wondering what would be the responses, because I was hoping that maybe if most of you are doing computational research, that will be actually much less of yeses, because you are much more proficient at using software and data, and your research is more reproducible. But it's interesting to see that it's nonetheless similar to what you would see in other disciplines. I will then show you what's globally the responses afterwards. But thank you so much for participating. And now that's a bit maybe a bit more personal question, but nonetheless important, and I hope you can answer it honestly. I will not be bringing anybody on the spot, I promise. Have you ever experienced difficulties reproducing your own experiments? If you'd like to share, of course you can, but thank you so much for your responses, and also for your honesty. I really appreciate that you're perhaps more honest crowd than some, in some other disciplines. That's very useful to know. Indeed, most of you say that you have difficulties reproducing your own findings. That's normal. We have to be mindful. That's why we are here, to learn about sustainability of software, methodologies of data. Why I wanted to bring this up, I will come back to my presentation. Thank you for your input, and actually what you showed me is something that I thought that you will say more no's, but that's the global responses of survey of all scientists across the globe, done by Nature, now a bit long time ago in 2016, but the answers are kind of similar to what you have said, that 70% of scientists who were surveyed had indeed difficulties in reproducing somebody else's experiments, and 50% failed to reproduce their own findings. And that's across the globe, across the disciplines, across the different communities. And just closer to home, I was just talking with Etienne before, who told me that you have also a working group on quantum, and maybe you have that story of you closer to home, about reproducibility issues in quantum research. It's something that was very close to me. I was based at TU Delft, where Leo Kouwenhove was based, where this all was happening, so something very close to my heart as well. So we can talk about this if you like during a break. But indeed, there is this recognition that we need a little bit more openness and accountability in research to fit that program of reproducibility. And just to reflect to the main topic, that I started with an almost personal story, but just to reiterate that reproducibility crisis and that lack of openness about data, code, software, the lack of sustainability of that, are just a few examples of problems with sustainability of the research ecosystems as such. There are more of that, as I mentioned at the very beginning. But for the rest of my talk, I would like to focus on solutions rather than dwelling into personal stories and problems. So Coming back to the main part of my talk, I would like to talk about open science, which in my view can be a transformative force to make research more sustainable. And what I mean, with open science, and I would like to walk you through that examples in the rest of my talk, that's about making research data, so data, software, other research outputs, also protocols, methods, methodologies, openly available to others, sustainable as well in the case of software, perhaps that's more important than data. What we did, the provenance, what we have done with the data and software, how did we reach our conclusions, but also crucially, to make the tools and infrastructure openly available and sustainable in the long term. But also, how through open science we can sustain people and collaboration. So ideally, we would like to reach a situation where people like Tim, like my colleague, who really cared about reproducible research and didn't bound into the pressure from supervisor, like just reproduce the data. He actually cared about good quality research outputs, are not pushed outside of academia, but are actually motivated to stay in science because they do good quality research. So all those topics, from people and careers and collaborations to really focusing on the research output, in my view, can be really aided the sustainability of that for open science. And what is open science? For that, I would like to also reflect with you on your own experiences. And if you could once again go to the Mentimeter. And the question is, how often do you do the following? And we have various options, and if you would like to choose 0 for you never engage in those practices, and 10 for you always do. Now we'll wait for a few more responses. Let's see before there were more people participating.
Quick question.
Yes?
Published peer reviews, does that mean that I publish the reviews of others, or I publish the reviews I get?
Did you publish the reviews that you give to other people? Sorry, that's a good question.
So it's
Thank you.
not
Yeah.
anonymous reviews.
No, it's about making them available, yes.
Okay.
Yeah.
Thanks.
That's a good point, and I should have worked on making that statement a bit less ambiguous for the future. Thank you for that. Thank you so much for your contributions. And again, I have to say I'm impressed. You are very much, I have the feeling I'm talking to a crowd of converted people who already engage in a lot of open science practices. These are all open science practices, and I'm really impressed that so many of you are publishing papers, open access, publishing preprints, publishing research data, making software available open source, and especially that, that's when you talk to, let's say, other types of communities, that's usually much lower, so not surprising coming from you guys. Methods, protocols, peer reviews, making teaching materials openly available, short slides and lectures. Actually, I don't need to explain to you what open science is because you clearly know very well. That's just a diagram which shows that, but you've already mentioned many of those practices. So instead of explaining, that's really an umbrella term for all of that, and that's deeply rooted in research reproducibility, in research integrity topics that are indeed at the core of that. We try to address them with open science. But what I would like to say, maybe focus more on the why first, and I think that's something that you probably came across as well, since you already are engaged in so many practices. There are different schools of thoughts why open science is important, that can be presented again in multiple different ways, but just wanted to mention some of the arguments that people often use. Some say that knowledge, as we create as human beings, should be made available to everybody. That's the driver for open science. There are many researchers, especially from the hard sciences, to myself, that speaks very much to me, probably to some of you as well, are of that school that knowledge creation is much more efficient when we collaborate with one another, when science is available to scrutiny. So, for example, in my previous story, if the data was available, hopefully science would have self-corrected itself faster than after 6 years. There are some people who argue that the motivation for open science is to basically make the research process more efficient. So if we have good infrastructures, if data, when we create data, when we create software, we can already assure the sustainability issues from the start, then actually everything is much more efficient. We don't have to worry about anything. So there is this infrastructure driver for open science. There is this public argument that because lots of science is funded through taxpayers' money, it should be available back to taxpayers. And also, there are people within open science communities who engage in open science practices because they are frustrated about the lack of recognition for good quality research. So they think that the metrics that we currently use to measure progress, to measure the impact of research quality, so as I mentioned before, the impact factor, H index, and so they are not useful. So we need different kinds of measurements to assess the impact of research. So just to bring about those drivers for open science. But most importantly, there are selfish benefits for practicing open science, and I'm sure since so many of you already engaged with that, you are familiar with them. But just to show a slide coming from the European Commission, let's not call it a benefit compliance with funder mandates. That's not a selfish benefit, but that there is the greater transparency in the research process, increased visibility for researchers if your research is openly available, potential impact of your researcher, greater efficiency and value for money, as I mentioned before in that story that I have cited, as research doesn't need to be repeated and we can easily make it available for scrutiny. There was lots of papers which demonstrated that if you make your science available, the citation rates of your work are higher, but also greater opportunities for collaboration because people see your research, but also can trust your research. To me, to be honest with you, I would say that from the pragmatic school as I am, I see time saved as one of the biggest important benefits of open science. So that's a selfish benefit. You as yourself, if you make your methods, your data, your software sustainable, you are the one who will benefit first from your open science reproducible practices. And now how, I guess the core of the arguments, we've addressed the why, we have explained what it is. And people argue that open science requires culture change because that requires all of us to move together, to commit to that. And to change cultures, again, I'm basing that on a paper from somebody else. It requires policy to make it required. That requires incentives to make it rewarding for people, value of their time to engage in open science practices. That requires community commitment to make it normative. You do it, but also all your peers do it, so you can do differently. Experience, make it easy, don't make it troublesome for researchers. And also infrastructures to make it possible. And in the rest of my presentation, I just wanted to walk you through a couple of examples of how can we make it happen and how all those elements can come together. And just also one thing to say that as in open science practices, I will be referring mostly to the work done by others, and I will give credit where it's due, so you will always find the credit and links at the bottom of my slides. Again, the policy make it required, so the first element. I will not bore you because maybe just a show of hands, have you experienced funder mandates requiring open science? Or maybe who doesn't? Who hasn't heard of open science mandates from funders? And you can see no hands. So I guess all of you are familiar with that many funders are now having mandates on requiring open access publishing, research data management. That's again driven by the arguments that I mentioned before. I will not go into that because you are familiar with that, and that's kind of bread and butter, that's not so interesting. What I would like to give one example of policy as an enabler, and here I wanted to quote an example from TU Delft, that's an institution where I was working with before. TU Delft created a research software policy, and maybe also to say why I bring this up. We had a lot of researchers at TU Delft who were quite engaged in open science. One of them was actually from that quantum researchers that I mentioned before, not the person that papers were questioned by another group of people. And they really pleaded several times with our valorization department, the people who help you to make patents and make money out of your research, that according to the TU Delft copyright regulations, whenever you make GitHub commit, like you want to make your software available or you make an update, you actually would have to, if you would read the law by point, by line, you would have to go to the people from the valorization department and ask them for permission. May I make this GitHub push, update my software? And he thought that it's ridiculous, and he threatened our IP department that unless you change your policies, I will write a script that with every Git commit, then it will file a new invention disclosure form to the valorization people, so to flood them with requests for IP assessments. And then, those IP people felt like the guy is right, the policy is crazy, and anyway, if somebody doesn't want to monetize the research, we should really make it possible that they can make it available for societal benefits differently. So I'm happy to say actually it was a nice example where the legal people, the legal folks which normally monetize science, got together with researchers, with people like myself and other colleagues who were more the policy advisors. And we developed TU Delft research software policy. And why I'm saying that's an enabler, because if a researcher from TU Delft wishes to publish this software under an open source license, TU Delft officially transfers copyright to the researcher. So basically, as long as you wish to publish your software openly, you don't have to go to those IP people, you don't have to do valorization reports or assessments or so. So that's actually, I think, something very much empowering and enabling open science. So that's why I wanted to mention that the policies can actually be your friends, if they are done well and if they engage researchers aboard from the beginning. And something hopefully that you are looking forward to see about incentives, so how to make it rewarding. So it's just not that one extra thing that we have to do, but something that makes us more happy and excited about doing. And here I wanted to give a quote from in the Netherlands, we have quite a progressive Minister of Science, Education and Culture, Robert Dijkgraaf. He was actually a researcher himself before. And at our Recognition and Rewards Festival this year, he reflected with us about all those issues in science that I mentioned at the beginning, the pressure to publish, the strange metrics, perverse metrics and so. And he reflected that, saying that since we have created the current recognition and reward system in academia ourselves, it is also us who can change it. And I found it quite empowering. Lots of people really got engaged. And in the Netherlands, at least, we have a national recognition and rewards programs where people really start to put open science, for example, in tenure track of researchers. So that becomes important. If you practice open science, we really care about it, we want to reward it, so making the careers more sustainable, making reproducible research practices, something that we care about, not the impact factors of your journals and your publications. And some of you might have heard, there is also, so that's not only the Netherlands, there is actually a European national global movement of and they are working together on trying to change that assessment of research. How do we reward and recognize contributions? So that's about the diversity of outputs, but also practices and activities, so that we have this concept of a researcher, and here we have actually a nice saying in the Netherlands of a five-legged sheep, something that really doesn't exist. A researcher now has to be an excellent at doing good research, excellent at publishing papers, securing grants, be an excellent supervisor, excellent teacher, and now, be excellent at data management, excellent at open science, excellent at sustaining research software, God knows what else. So that's also about recognizing that concept of team science, that within effective research team, perhaps you don't want to have all the bunch of people doing the same, but maybe you want to have some researchers, some research software engineers, some data managers, people who can really help you to make science a bit more efficient, and recognize all those careers. And again, focus on the quality and impact of research instead of false metrics like impact factors of papers. So what is happening? And here I wanted to bring an example from NVO, that's the Dutch Research Council where I'm sitting currently. What we have introduced is a different way of evaluating applicants. So when they apply for grants, traditionally, that we would ask about what's the impact factor of your journal, what's your H index and so on. That, of course, doesn't make any sense. So to practice what we preach, we now have removed the possibility of mention whatsoever of journal impact factor and also of H index, and the assessment committees are trained to avoid looking at that, to make sure that researchers don't mention this in their applications. But also we introduced something called evidence-based CV. So you are not listing endless numbers of papers with their impact factors, but you are asked to list 10 key outputs. So that can be anything. It's really a huge and exhaustive list. I did not even anticipate how big it was. But it can be data sets, methodology, conference presentation, tool, lecture, workshop, etc. And there is a special attention to open science. Are these outputs openly available? So that's the question that you have to answer. And you select just 10 because we want to focus on quality, what really matters to you, instead of quantity of your outputs. Another example of rewards, that's again coming from home, from NWO, the Research Council in the Netherlands, is we also have a dedicated open science fund, and that's to stimulate and reward open science practices. That's something that sometimes you could say, I don't have to do extra. You get dedicated funding to actually make your research openly available, to engage in open science practices. So that's 50,000 euros per project, and it really can be anything. There are no strings attached. It's not research. It's really open science practices. So it can be, I want to devote time to make my software sustainable. I want to make my data set available. But also, I want to engage with my community to develop, I don't know, standards for how do we publish data set within this community, for example. There is also this data management and software sustainability section for projects, which work on research software. And we have more and more of them who actually really want to increase the sustainability, like community engagement, availability to build on research software. But we also ask about the open science track record of the applicant. So if a professor who has never engaged in open science practices, because they didn't care or whatever, suddenly applies to us and says, well, I would like to do that, that's fine, but you have to explain why beforehand you have not practiced open science and why do you want to change your practices now. So what was your reflection? What made you change your mind all of a sudden? We really want to focus on that reflection with researchers. And all proposals are published, also those which are not successful. And applicants review each other's application. That's also to help people to appreciate each other's contribution and also a little bit teach each other how to be a little bit kinder and perhaps understanding when also being the reviewer. So these are the ideas. That also works at cross-fertilizing ourselves with ideas. So if you learn from an idea of a colleague, perhaps you will collaborate with those people. Just checking the time. And the other component of making open science the norm is also the community effort. And here I wanted to highlight an international effort of international network of open science and scholarship communities. There are now communities in 16 countries, 32 communities in total, more than 2,000 members. And these are really researchers, like I mentioned some of those from TU Delft, that colleague that was threatening our valorization center to write a script to file invention disclosure forms. People like this guy, but many, many others, many of you perhaps as well. There is an open science community in Paris, for example. So these are hubs where peers, researchers who are committed to open science come together and support one each other with their practices. So there are no good and bad answers. It's not that you are not open science good enough. If you are interested, if you would like to do something, you are looking for a peer or a helpful hand or somebody to brainstorm with, this is your crowd. These are people like yourself who would be able to give you a helpful hand or discuss with you, exchange practices. There is also, in case some of you is interested in those practices, or maybe you have someone who would be interested, the community themselves, they came up with starter kits, so sharing experiences with the others, how to get started with such a community. And they also even run an incubator program where they try to give some mentorship for support for the people who would like to get started with open science communities. And that's really by researchers for researchers. And also wanted to reflect, that's a person who really influenced me when I was back at the University of Cambridge, where you might not have the wish or the will to start a community yourself, for example, or be engaged in a community effort. Maybe you are not a community person, that's fine. I think it's important to start small and think about influencing your own peers. And here I wanted to bring up the example of Professor Florian Markowitz from the University of Cambridge. He would say very often that some people will come to him and say, well, I would rather do real science than tidy up my data. I'm sure that probably you have heard it one or another time in your career. And his response, and he was really convinced about it, that if you don't work reproducibly, you are not doing science at all. And also, if you start early on, you don't waste your time doing something, badly in the long run. So actually starting small, making the small steps makes a difference. And why I mentioned him as an inspiring leader, he actually even wrote a paper. I can certainly recommend you. It was one of the papers that really inspired me in my career as well, about 5 selfish reasons to work reproducibly. Like he talks about those kind of statements, but also about the practices that he instated within his own research group. So whenever he says there is a new applicant to his research groups, he first asks people, please read our ways of working. Do you subscribe to that? Do you care about reproducibility in science? Because that's what we care for us, that's what's important for us. And I think those people can really make a difference, like Florian, to make open science a bit more normative. And finally, experience, how to make it easy so that it's not such a pain to do. And here I wanted to mention 2 initiatives. One again is close to home, that's funding that we as NWO, the Dutch Research Council, have enabled to institutions, quite a lot of money actually, to start, first of all, local digital competence center. So that was kind of a start of money to institutions, which allow institutions to hire data managers, data stewards, research software engineers. And most of them, what they did, they hired few people. For example, at Delft, where we also started such a competence center, we had a pool of 6 research software engineers and 4 data managers that were available kind of centrally. But researchers could write like a mini application, 1-pager. I would like to receive their support because I have a project on blah, 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 and I would like to make my software more sustainable. I would like to improve my workflows for data management. You don't have to have the skills, and that's fine. They would join your research group and help you, teach you the skills while also improving your workflows and processes. So that's a kind of an interesting concept where we can grow these in-house skills, capacities to help research communities with their transition to open science practices. So that's more the infrastructure scope. Make it easy. If it's easy, if you don't have to think about this, that becomes just naturally embedded in your processes. And another thing that we also funded is thematic digital competence center. So this addresses domain-specific challenges and coordination. If you like, there are some problems, processes which cross the borders, like for example, interoperability of research data. That's a topic which we should not be doing locally within the communities, but work more collectively within the domain. So that's also something that we have funded, and we have these expertise centers at the domain levels within the Netherlands. And finally, hopefully something that addresses also the topic of today's seminar. The Netherlands eScience Center launched a call for sustainable software. And that's really aimed at supporting communities that require that research software, which is important for them to be preserved, to meet higher quality standards and to ensure that continuity of that software for the advancement of the research. So that addresses what you've mentioned at the beginning, that there is no funding to make software sustainable. Actually, there are some efforts in the Netherlands, in Germany, I have heard as well, to do that, and hopefully in the future we will also be able to invest more funding in that. And what people get in return, they receive a 2-person per year in-kind support from the eScience Center. They have a team of research software engineers, very qualified people, to really help researchers, communities sustain the software. So they are professionals who can make it a little bit more easy to maintain and for the community to engage in future development. And finally, I also wanted to talk about infrastructures, because it all should be possible and it all should be made easy. So just in the connection with openness, I also wanted to highlight a statement coming from 40U Research Data, when that's a data and software repository in the technical sciences. And that's the statement they have published when they were announcing the move to free and open source software from a proprietary system that they used before. And I would like to read it out because I think it's quite inspiring and that's connected to the software sustainability topic that you are discussing here today. By facilitating community-driven development, we can work towards sustainable infrastructures which are agile and able to quickly respond to changing needs of the community. By co-developing and partnering with the research community, we invest in solutions which are valued and needed by the community. So that was their motto for switching to free and open source software from proprietary solutions used before, because it's more sustainable, it costs us less in the long term. That's something that we can maintain and co-develop with the community. And also to mention, there are organizations like Invest in Open Infrastructures, which specifically make funds available to support such initiatives. So here you can say that's a small amount of money. They make available funds from $5,000 to $25,000, but they received 200 applications from across the globe from people who wanted to make the infrastructures more sustainable, more open, more available to others, more community-driven. All the proposals were again openly available, and the peer review assessments of those proposals were also publicly available to again promote this accountability but also cross-fertilization of ideas within the community. I would like to end up my presentation with saying that I hope I convinced you with some of those arguments that change is coming, that there will be more activities and support towards open science. And finally, I wanted to share with you some good news, at least from the Netherlands, but I'm sure that will be coming in other countries as well. I have cited some work from the European Commission. There is lots of work happening in France, in the US, in many other countries. There was this letter from the Ministry of Science and Education in the Netherlands where they really stated that they believe that open science should be the norm. We should really be investing in it as a country. And they made 20 million euro per year available to accelerate this transition. So that's how my position actually came about. There was a dedicated team created within the Dutch Research Council to really invest this 20 million per year in community initiatives to promote open science. So I hope that for now we are working on a work program, so funding schemes of what we can enable to make open science sustainable. I really hope to address your point also about funding for sustainability of research software. That's one of our big things that we try to push through. At the moment it's still confidential because our board has to discuss and see our proposals, but hopefully in later this year or early 2024 we will have some good announcement to make also about sustainability of research software, of infrastructures, of recognizing and rewarding open science practices. 20 million euros per year, it's not a little amount of money, hopefully, and hopefully it will make a difference. So, just to summarize, I hope I managed to bring at least some arguments that open science can lead to more sustainability of research ecosystems. And just to summarize, what I wanted to say that open science is really a collective action. That also means that each one of us can really make a difference. Each one of you can make a difference. And whether that's sharing of data, of software, making your software sustainable, as many of you already are doing, so that's really great to see. Whether that's agreeing on workflows locally, how do we make our work reproducible, what do we expect of each other, so that's making that open science normative, reproducibility normative. But it's also about giving time and space to each other to engage in those practices, to recognize that actually what we are doing, if we care about the quality and impact of science as such, of research as such, of sustainability of our research activities, that's really important to give each other time to engage in those practices. And hopefully with time this will be more and more rewarded. But also the encouragement and appreciation. And here I just wanted to reflect, I would love if my colleague Tim, whom I mentioned at the beginning, stayed in academia, because I think we need people like him who really care about reproducibility of science and will dare to dig into that problem and try to solve it. That's a real scientist in my view. So that would be great if people like that could also stay in academia. But also, if you have that possibility, think about engaging in local activities. And I was talking to Thierry before about your community. I think it's impressive. You have an amazing power that you engage with the community across the globe, and you are addressing such topic as sustainability of research software. I find it brilliant, so you are a great example here, and I think for other members of scientific community, how to proceed, how to make a difference. I think your activities are really remarkable, so engage in local initiatives. And if you have a chance to ask your rectors, the people in power, whoever you are responding to, for support, please do, because maybe they are thinking about this, but they don't know if there is a need. Maybe they can give more funding available for research software engineers, for data stewards, for indeed recognizing those practices within the research community. Finally, a thank you slide. I wanted to thank lots of different colleagues. I probably haven't mentioned all of them. Each time I came to the presentation, I wanted to add extra names, and I thought that's just will never be sustainable because there are so many people to thank. I wanted to mention one name, my colleague Maria Cruz. She's the program leader in the team of Open Science NL. She's actually responsible for looking after open research software, and if she was available today, I would have definitely suggested her as a speaker instead of me, because her job is to think about sustainability of research software. So, amazing speaker for the future. In case you are interested, she's much more competent than I am. My boss Hans, and also all the other team members, various colleagues from the past, who have really inspired me in my work, but also the organizing committee, the organizers today. You have spent a lot of time answering to my emails and having discussions with me in preparation for this talk, so I appreciate it. And thank you all for your attention and for your patience if I'm not the expert on big data and computation. I really appreciate that you have devoted some time to my talk. Thank you.
Okay, thank you very much, Martin. We have enough time for questions, remarks, comments. Yeah.
So I agree with most of what you say, and I enthusiastically endorse it, but there are a couple of aspects of the open science movement that I find to be naive and troubling, because they assume that human beings are all objective and are not going to be making use of things like somebody else's not approved proposal to write their own proposal, because then that person doesn't have the opportunity to submit it another place and pursue that idea. And getting funding directly translates into being able to get students and postdocs in order to be able to pursue that idea. So I would hope that the open science community would reconsider publication of someone's idea that did not get funded in the first place, because that can lead to a great deal of damage to the career of the person who had that idea in the first place. And the second one is publication of peer review, because I don't know that there are many human beings who don't feel resentful about reading negative reviews from someone, and they will have negative feelings towards the person who wrote such a review. In fact, a peer review, if I am the reviewer for something and I know that my review is going to be able to be read by the person and they know who I am, I will not be as candid in my review as I could be if it was an anonymous review.
Yeah, that's a very good point, and I appreciate what you're saying. Maybe just to clarify with the Open Science Fund, where I mentioned that researchers, we publish the proposals, people are asked for their consent if they agree for their proposals to be published, and maybe also to say that's something very specific, that's something with regards to open science. We don't do that sort of experimentation, if you like. We always ask for feedback. We ask people how they thought about those processes. That's not across all the different grant schemes at NVO, and I agree with you, there is sensitivity about it. So that's not to say that all the proposals we ever do should be made available openly. With regards to peer reviews, there have been some experimentation. I think there are still discussions in the field. There are some journals which make the peer review process completely open. Where you sign the peer reviews are open, available, and everything, if you like, is in the open. I did hear some opposition about it, and I think there are still ongoing debates. It's just one of the examples of open practices which some people experiment with. it's not clear whether this would be the thing and whether this should be available across the spectrum. For example, there is evidence that when people sign their peer reviews and make them openly available, they are indeed more considerate and kind, because you want to put your name under something that you have really did a good job, that you did a good peer review effort. So there were some evidence that signing a peer review, making them public, increases the quality of the peer review process. But there were also important voices from the community, so I fully hear what you say, that especially for early career researchers, it can be very intimidating to sign their peer review and make them publicly available if you are reviewing a paper from a powerful scientist in the community. So absolutely, I understand your concern, and I think that's why there is lots of experimentation ongoing, but it doesn't mean that everything is right. Maybe just one idea that I also wanted to share, that's something that is not public yet, but something we are working on within the team, to also fund dedicated effort to support research on open science practices, so that all those experimentations, if you like, we investigate what kind of effects does it have, what are the positive consequences, but also what are the negative consequences, what should be continued, what works, what doesn't. So I absolutely appreciate your comment, and I agree with you that it doesn't work for everything, doesn't work across the spectrum. We have to be careful also for the unintended consequences. So that's a very good point.
Yeah, thank you very much for this talk. Another aspect that I think is relevant in our community, there are concerns about, on first place, IP protection. So we are a community that is working very closely with industry, where there are commercial interests that have rights to be protected. And there is also the aspect that is very important also at political level of sovereignty. So there is a little bit of contradiction between making everything open and protecting the interest of both the industrial partners involved and the funding agencies and the regions for which we are actually working. I don't know if you have any thoughts on that.
I think you are very right, and when I was working beforehand at the Technical University of Delft, that was our bread and butter, those kind of discussions. And I think there is, in a way, you can manage those conflicts, that openness and commercialization are not necessarily against one another. You can always think about where it's useful to have things in the open, where they should be protected and commercialized. And for example, maybe I can give some examples, I can send some more information afterwards if you like. There were some movements within pharma companies, so the biology sector where I'm a bit more familiar with, where they wanted to make the drugs databases, so the early process of discovery, openly available to everybody. That's because that we benefit from the global initiation of testing of ideas, of testing various drugs for various diseases. But then, when the process advances to a stage where you would like to make it commercial, then it's, of course, that's a lot of investment from, for example, pharma companies to bring something for the market, to the clinical trials and so. So there are parts of the process which are open to anybody, to basic science, and there are parts of the process which are closed. There are various combinations how you can combine open science with commercialization. And sometimes you're right, the interest of commercial players to, for example, invest a lot of funding, they have to be taken into account, and maybe you can't make all the things available. But for example, you can think about synthetic data, you can think about making synthetic data available, even if you, for example, we had at Delft, we have been doing lots of research into, oil industry, which is another question about sustainability, but I don't want to get into details. I'm also very passionate about this topic. But about the fact that if they share the raw data, that the company would reveal their locations of their resources and so. But on the other hand, some scientists, to make their models reproducible and make their findings, algorithms reproducible, they were making synthetic data and making those available. So that's one way you can try to make it a bit more available for others. But indeed, sometimes, I think what's important is to think about as open as possible, as closed as necessary. And with our IP department at Delft, actually, we had really fantastic people who were willing to engage in those conversations. The primary thing was that you don't give away your IP, and I don't want to give names, but it was quite common that researchers would make, let's say, deals with commercial partners, in a conference without the help of their IP, and then you give away the IP of a university, because university is such funded by public money, the default position should be open. Of course, then if you have a commercial party involved, you have to find the right balance, you know. What do we make open, what we don't make open? But then if sometimes people who, I'm not saying that nobody has experience, but there were researchers who just didn't have, and they were happy, oh, this company wants to give me money to hire a PhD student. In fact, they only take a gain because the PhD student is very cheap labor for them, and the PhD student probably will not get a PhD thesis out in the open, which is a problem for them because then they can't show the research that they did. You know, so it's about really helping and supporting one another, understanding the interests of both parties and finding the right conclusion. I don't know if I answered your questions, but I'm very much aware of the tension. It's not about making everything really open. There's also a lot of issues about indeed sovereignty, knowledge transfer, knowledge security, and they all have to be taken into account for very good reasons. So we should find the right balance indeed.
I really enjoyed the talk, and I like how you point to the necessity for professionalization of creating openness in science and investment, because these are, I think it's often underappreciated how difficult it is, even by people who are, you know, of goodwill, who want to make their science open, how easy it is to do it badly and ineffectively. So I'd like to sort of provoke you into a response, I think, on something that I think you sort of touched upon, but didn't really go into in detail. And one of those things is making science results permanently available. Right now, there's a lot of difficulty. Even when you archive your data, you archive your software scripts, you archive all the products of a project. You might have a repository where you make all of that stuff available. Sometimes the data masses are very large, so you need specialized archives to make this available. Sometimes they only guarantee the availability for the duration of the project plus N years, and then it disappears. It's really very difficult to find a solution for data permanence, and that, I think, is not something that is being addressed systematically in terms of the infrastructure investment. And there's a related issue, which is when people, you know, when you make your data available, it's often, especially in computational science, it's essentially encrypted. You know, without the software scripts that you use to analyze the data and reduce it and transform it and so on, you can make the data available. It'll be completely worthless to everyone. But now you have a new problem because those scripts, software has a finite lifetime. So someone takes your scripts or your software 5 years from now, they might not have the libraries to make it work. They might not have a platform to make it work. So that's an extremely difficult problem to address. You can do everything right, and it's still going to die in a few years. So I'd like to sort of ask you for your thoughts on what's being done and how this is supposed to be done.
I think you are very right. You know, you are touching exactly where the problems are. We don't have all the solutions to all the problems. You are right. You know that long-term sustainability of data storage is one of the issues. One of the possible solutions, again, it's not easy. That's on a case-by-case basis. Is data curation. So really thinking about which parts of your data sets are worth to be curated. You know, is it actually worth to be curated? What exactly is that key thing from your research outputs that you want to preserve? That's indeed not all the experiments that you ever did, you know, that should always see the light, you know. Maybe just one example, when I was working at Cambridge before, they had amount of data that Cambridge was creating per year and the amount of data that was ending up in the repository for research data that was of no concern, at least at that stage, to IT people. So they say, well, we can maintain it, it will be longer, it will be easier and cheaper for us to keep it in the long term than to be evaluating which of the data sets should be deleted or not. The same problem, maybe Ricardo knows more about it. I'm looking forward to your talk. I spoke with colleagues from Zenodo, that's the repository for data, for software, for anything based at CERN. They said that their repository, it's actually not an issue for them, you know. That's one issue of the storage space itself, but of course you're right, it's the issues of long-term sustainability. That's true for data, that's even more true for software. I don't think there is any solutions to that problem. You know, for data sets, there are techniques for data preservation, so to migration of file formats, and so especially if you use open formats, so there are techniques what people use. There are also ways that much more complicated. I agree with you about software preservation, making software sustainable, and I think we'll be talking about it today. I'm looking at Ricardo, probably his talk will also be addressing some of the solutions. I agree with you. There is not a magic button, we have solved the problems, and I agree with you that data without software is often not very useful to anybody. So that needs attention, that needs sustained effort and investment and recognition that it's not easy, it takes time, and that's effort which should be funded again. So coming back to the initial comment of yours, that we need to recognize that it costs money. I don't have a magic wand, I'm afraid, that's a very good point, and I appreciate that you raised those issues.
So just to dovetail on the last gentleman's comment, again, yeah, if you publish a data set in a software stack, it becomes an unfunded mandate for the investigator to maintain to make it useful. And I think it's absolutely important, and yet our funding and reward structures don't necessarily encourage that long-term sustainability. One thing we've talked about in previous communities is the idea of bringing back professional data librarians, where organizations or communities can maintain infrastructure and research staff to be able to do that transition from the primary researcher to somebody who's skilled in actual curation and maintenance of these data sets and software stacks, to be able to help them go forward. And I just think it's an important task.
I totally agree with you, and that's what we, at least as in the Netherlands, we recognize that that's what we want to fund. We want to fund data managers, data stewards, research software engineers, but beforehand, what I mentioned, that organization for TU research data, that's actually a dedicated domain-specific repository whose job is exactly to maintain the data set for researchers, but it's not your responsibility, it's somebody else's task, of course, funded by the community as a whole, because the community recognizes the importance of having those professionals with those skills to be able to preserve research data in the long term. And I think we will hear later on about what kind of efforts are available to also make the software available more in the long term. But absolutely, you're right. I do think that it shouldn't be the effort of researchers themselves. We should have professionals who have the right skills to do that, and they should be paid to do this job because it's important for us as academia. So thank you for the comment.
Thank you for your talk. Yeah, as you said, we are more and more pushed to keep data, software, and all scientific data. As you also said, it requires a lot of infrastructure and a lot of professional skills. And some of the data are reused, and I guess a large fraction is never reused. And are there evaluation of the cost, like how much it costs to keep all this data versus the usage that is made of the data and the science that comes out of the stored data?
I think you're very right. That's a very good question. That indeed, what let's say from the professional point of view, that's part of the data curation. Deciding, what data sets are valuable. That's not easy. You need to have experts who have the disciplinary knowledge, and sometimes you just don't know. Like even if you think that this will not be useful, maybe in the future for somebody else your data set can be very helpful. So there are some techniques, there are some tools that help people, professionals, to help make decisions about what to preserve. What perhaps is not so helpful to preserve. But it's not always black and white, as you can probably imagine. It's difficult to predict what will be in the future. In general, I think indeed data sets and software, they should be available not only for the reuse, but also for the reproducibility of the research process, And I agree with you, we sometimes have to make difficult decisions, especially when I guess you guys are working with large amounts of data. Sometimes it may not be feasible to preserve the data. Sometimes you may want to describe, how the data has been created, the model that you have been working on, or the software might be more important for reproducibility than the data themselves. Again, it's really case-by-case basis, and absolutely I agree with you, but that's why in many institutions, I think all over the world now, people are hiring so-called data stewards, people who can really help you, to guide you and make those decisions, who have a little bit more experience in asking those questions about what can be useful. But of course, they have to do it together in the discussion with researcher, the person who knows the data themselves. There are no black and white answers for that, but absolutely I agree with you.
Well, thank you very much. It's a very good condition, but just an announcement from my association, Aristotle, because we are organizing next October on the 18th a seminar concerning the value of research data, where we address some of the problems. So it's a French seminar, but I think we try to come back to the value of the data, the research data, in various fields, and it is one of the topics we would like to address. So I think we can thanks again Marta for this very important. And now we have a break, so I just recall you, if you don't sign the paper, please sign the paper on the desk. And we have about 20 minutes break. And we start. Thank you. Okay, so should we start with the first session after our keynote about software sustainability? And so we welcome Christian and Daniel from Artigen Zambia. And the talk is about software sustaining performance portability for the exascale area.
Thank you all for being back here. I'll talk a little bit about our plans for how we want to sustain Cocos, the Cocos ecosystem. This talk by me and Damien, who is my colleague from Oak Ridge for Cocos Core. I'm not going to talk at all about any technical details whatsoever, but this is going to be more like from a programmatic perspective. If you really want technical details, there's dozens and dozens and dozens of recorded lectures and talks and other things from me. Yeah, I mean, I'm very proud of this picture, right? I worked really hard on this for a long time, and so I'm showing it for like the last 5 years, again and again. But I mean, that's a core idea. So it's right. All these things, all these applications and libraries and whatnot, write to Cocos, and we take care away all the pain from you, almost all the pain from you, and deal with all the underlying architectures. Now, I think that's working really well, but from a sustainability perspective, right, it's working really well because we've been working on this really hard for a really, really long time. A lot of people don't know that, but the original name Cocos started in 2003, and that was a project which actually is called more like the Cocos kernels now, the math libraries, linear algebra support. It started in Trinos, and the idea there was to isolate, like math libraries for the rest of the solver packages and whatnot. They actually then added already in 2008 the first concept of, kind of adding support for GPUs when CUDA came out. And that still was only like these math libraries. And then in 2010, this project started with Cocos Array for like, data abstraction, and that is actually what then evolved to Cocos Core, the programming model. So the first release of, what currently most people understand as Cocos, right, actually started as Cocos 2.0, because there was this other thing which then was a complete different code base and was completely abandoned and rewritten later. We then worked on applications, lamps and Trillinos and stuff like that, right? That was really important to get the first kind of real users. And actually the Cocos team rewrote that. That wasn't like the application teams rewriting them, it was us doing it for them as a demonstrator. And that was pretty successful. We got all kinds of other things showing up. In 2013, we started working on AMD APUs. We worked really hard on those. They, never made it into real product for compute. In fact, it was really hard to get anything to work because there was a little trick in the Linux kernel where you had to modify the kernel to make it work, and nobody knew about that except one guy at AMD. But that's a different story. But we worked really hard on that. In fact, we wrote multiple backends for AMD GPUs before the HIP thing even existed. All of these things are deleted, right, because they are not supported anymore by anybody. We worked really hard on Xeon Phi. That took a while. That actually was a really busy time, with all the KNL and Xeon, whatnot, vectorization, etc. This was actually the main thing for Cocos, right? The main thing for Cocos was we wanted to figure out how can we run on machines like what was it? What was our Xeon Phi machine? Somebody help me. Trinity, exactly, Trinity. It was our big Xeon Phi machine, while at the same time we got, Summit and Sierra coming along.
It was only half Xeon Phi.
Huh? Yeah, I know, it was half Xeon Phi, because, delays, right? and budget constraints, whatever. So we worked really hard on that, and we made that, finally figured out how to work, when, that line also went away. This is actually a recurring story, right? The Cocos core team does a lot of work on things which, exist for a couple of years and then they go away again. But the nice thing is, all our applications didn't care about that, because we did all the work, all the extra work, unnecessary work, or maybe necessary work, and they didn't have to worry about too much. And when came, that's it, Trinity came, where Summit and Sierra came, ECP started sometime around that, and we worked a lot with people, and finally, the current kind of generation of AMD GPUs came along, and in 2020 we had finally these new free backends for all this other stuff like Intel GPUs and whatnot. Now, the Cocos ecosystem today, right? We have these. The Cocos ecosystem is really like a collaboration of different projects, right? Which are really tightly working together to make sure that all of it kind of fits together, works together, and is one coherent whole. It's kind of like the CUDA ecosystem, or one API for that matter, where you have all these different pieces which really interlock together to give you one solution to do all the things you kind of need to write applications. And that's like Cocos kernels, Cocos core, which is the kernel execution and kernel data structure, but also support, right? ECP funded explicitly support for us, write documentations, develop training material and whatnot. That was absolutely critical in order to increase the, the amount of people we could support, the amount of people who actually thought about using our stuff. And that's a big part of sustainability, right? You have to have explicit money for doing this. We spent multiple FTEs just developing our lecture series and stuff like that, right? It takes a lot of effort to do this right. It takes a lot of effort to do documentation, right? And if you don't explicitly fund that and just want us to do research, we're not going to do that, right? There's other projects which are kind of on what nowadays one would call kind of incubation path. Cocos remote spaces for like PGASI models, like global arrays. PyCocos, which is the interoperability with like Python. There's stuff around resilience and Fortran interoperability. And then if you zoom a little bit out, there's all these other things which sit on top of what we call the Cocos ecosystem. Things like Trillinos, Petsy, which is using Cocos, use Cocos to run on Frontier, AboX, Kavana, and so on and so on. There's literally dozens or even hundreds of these projects out there which now use Cocos and give you other capabilities, which aren't part of the kind of core ecosystem piece. And that led to, all of this is accompanied by this huge growth of the Cocos community. We have about 1,200 people in our Slack channel registered, 1,200 developers which bothered to do that. That's pretty clearly not all of them, because I know that at least half of the people, or 80% of the people at Sandia didn't register. And apparently, even like students here at CEA who've been using Cocos for the last couple of years have not heard about that and registered to do that. The other thing is that our developer base, right, has been kind of diversifying through ECP. We have now getting a lot of contributions from Oak Ridge, right? In fact, for Cocos Core, they do the majority of our contributions over the last couple of years. We also get contributions from like Argonne, Los Alamos, Berkeley, and CSCS. Now, that is where this ECP funding, right, came in. When in 2019 or 18 or something like that, right, ECP leadership came to me and said, okay, we now announced that we have, AMD GPUs and Intel GPUs coming. Does that cause a problem for you, right? Do you need more money to make this really robust and work, right? And I said, considering that you gave us 2 new completely machines we've never really supported before, maybe we might need some more stuff. And I said, how about you give me, more money, and I give that money mostly to Oak Ridge and maybe a bit to the other labs, and say, we're actually going to have people at the place which field the machines to support them. And they said, oh, that's a great idea, we're going to give you money, and that's where we got a really good team then at Oak Ridge in particular together to do that. And that's what you see here, right? In the 2 years before ECP funding, 95, 96% of all development in the Cocos ecosystem happened at Sandia, right, with some random contributions from outside. After that, only about a bit over a quarter of the contributions for Cocos Core came from Sandia, and a good chunk from the other DOE labs. And even the rest right outside of DOE increased quite a bit. So one question people have been asking a bunch of times is, right, like, why did we go a library approach, right? And how is this like different from, say, one API or like the OpenMP and OpenACC kind of compiler thing, right? And we did this library approach for some actual reasons, right? One of the reasons was we didn't really have much expertise in writing compilers, so that's not our core competency. So we didn't even attempt that. But there is real benefits to doing this library approach. One of them is we actually run with the optimized vendor toolchain on every platform, right? We're gonna run on Frontier with the Rockham platform, right? We run on Perlmutter with the CUDA platform, right? With MVCC or MVC++ when it gets ready, eventually. We run on Intel with the compiler they give us, right? ICPX, and we run with the Sybil platform. What we do is, right, we go to a vendor and tell them, what is the programming model you want us to use, right? What is the compiler toolchain you want us to use? What is the thing you support best? And that's what we use, right? One advantage of that is you can use these things immediately when the hardware is available, right? With the first toolchain the vendor gets ready, this thing will work, right? Assuming you give this to C++ compiler. These vendor toolchains also, what Greg said, right? We expose new hardware capabilities, right? Really early on. This being able to compile all of this and use that toolchain means we can also potentially expose that really early on through the Cocos ecosystem. Instead of doing some, compiler work and some third-party thing. It also enables us to work with vendors before their stuff is publicly available, right? If you actually would need to support your programming model or whatever through some third-party compiler, right? Then it's questionable whether you can do that during this kind of NDA phase with people. In this case, right, we just fork Cocos somewhere into a private thing, and we keep working on the toolchain. Full interoperability with vendor libraries. In Cocos code, right, you can call CUDA intrinsics right inside the kernel if you compile for a CUDA platform. That's something you can do, right? And we have a last thing, wider developer pool. It's so much easier to find people who have some experience with writing CUDA code or Sybil code or whatever than people who say, oh yeah, I implemented the programming model in LLVM. Right? Another piece of our sustainability story is the ISO C++ interactions. This is something we've been working on for a long time. The idea, and that was something we had as a pitch for Cocos from the beginning, is that in Cocos we can prototype capabilities which potentially can be standardized. Right? We can prove out capabilities, say, this is really useful for a large number of applications, and then go to the ISO C++ standard committee and say, here's a capability which really was useful across a wide range of HPC applications, different HPC areas. And actually give them an implementation. We can say we have implementation experience. We can say, yes, we supported this on all these different platforms with all these different tool chains, and go from there. It requires a lot of effort. MDSpan, which is our greatest success to date, actually getting multidimensional arrays into C++, that cost us 9 years from the very first proposal. We worked 9 years on that, right? For a good chunk of us, that's, I don't know, a third, a quarter of the total career expectation time, we're gonna have in this field. You can't do that with students, you can't do that with postdocs, right? You actually need people who can commit to something like this for quite a long time. Linear algebra, we learned how to do these proposals, so it goes a bit faster. So it's probably only going to be 5 or 6 years until we have it in. As I said, what you need in order to get anything into ISO C++ nowadays is you need usage experience and you need a prototype. You need to actually have this thing implemented. You have to show this does what we say it does. It actually meets the use case we want to meet. And you have to be able to say, yes, we have users who use this stuff for a while. The ISO C++ standard is not in the business of innovating. It standardizes practices which have been shown to be useful in the real world. Right? And so, Cocos in this state, right, if it's large enough, if it has a large enough user base, can serve as a proving ground for these kind of capabilities. We can innovate, right? We can do new things, and we can demonstrate, that stuff works, right, in the real world. Yeah, we got a bunch of successes. This capture, it's really highly technical, but that was a real doozy, real bug in the standard we fixed. Atomic ref is really important for atomic operations, and it's also highly technical, while the previous atomic is completely useless to us. MD span, linear algebra is in flight right now. We are doing wording review. We might have a shot at the November meeting to actually get it into a draft standard, at which point we're actually going to get all of class 1, 2, and 3, including mixed precision and layouts and whatnot, in a standard interface in the C++. Yeah, there's a couple of things. But the point is we need long-term engagement with ISO C++. That's really important, and it's an integral part of what we are trying to do. Now the other thing is that sustainment of projects, right, does something what I call a self-reinforcing cycle. Right? You start with a good product. If you have a good product, right, it's obviously easier to get more users. But more users also mean that you get more feedback, right? They discover corner cases which don't work. They try to use more platforms, more tool chains and whatnot. And if you then start supporting them, your product is getting better, and it improves, the usability for future users. It helps you getting more users, right? So that kind of reinforces itself. Having these users means you get more funding, right? Eventually, it makes it easier to get more funding. But sustained funding is actually very critical also to get users. The first question every new, user or customer who thinks about using Cocos asks us is, how do I know that you guys are still around in 3, 4, 5 years when I'm done porting all my applications? Right? And the only thing we can say is, yeah, we had sustained funding for the last blah 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 years. We have this many internal customers which depend on us. So it's fairly unlikely that DOE is going to turn off our funding, because that would cause all kinds of problems even just within DOE. But it's again a thing which reinforces each other, right? Sustained funding gets you more users gets you more sustained funding, and then the sustained funding, right, allows you to improve your product. And so all of that hangs kind of together. The thing here is that what that means is there's actually strength in numbers. Working together on one common product, right, on one common project, on one common solution, helps you make one really good solution instead of 15 half-assed ones, right? And that really helps for sustainability in the long run. Now there are a couple of pillars to that sustainability, which is also really critical. The first one is open source, right? Open source, we need open source, the projects to be open source in order to enable a wider set of contributors. It also is a risk mitigation for partner institutions. No one can just take this project away, right? I mean, in the worst case scenario, which is what I told the ASC program as our internal kind of program. Worst case scenario, if it completely breaks down, if a community breaks down in acrimony, and everybody fights everybody, we fork the project into our internal GitLab, and we continue developing it on our own. We're not worse off than having it done all on our own all the time anyway at that point. right? So the worst case scenario is the thing you do if you don't try to build the community. Permissive license actually seems to pretty critical to me if you want that interaction with industry. They really don't like GPLs. They've been complaining to us about that quite heavily, and permissive license gets you around that. I think it's more appropriate for like software technologies than maybe applications, but on the software technology side, I think it's pretty critical. You need the core funding, right? You need the kind of core sustained funding. You need a group of institutions which are really committed to the project and do this. Right now, we have on the NLSA side, Sandia National Laboratories, which is really committed to it. Los Alamos, kind of. Their strategy is a bit in flux sometimes, but the number of critical applications there which use COCOS has been increasing quite a bit recently. DOE OSCAR facilities, we got some commitment from them. In particular at Oak Ridge, we got some commitment that we want to keep funding some of the ECP people we have there. We're in talks with NERSC and ALCF, to see if we can do that too. DOE sustainability, which I think is now renamed stewardship. The direction there is still a bit in flux. It's not clear how much money there actually is. We'll see. CA, we are starting a project. We're actually going to hear talk about that. We're hoping that we have some kind of long-term sustainment coming out of that. Last piece, open governance. One of the things you also need to be able to do, right, in order to get other institutions to really buy in is you need to be able to say, yes, this is a partnership on equal footing, right? Everybody has a say in this. It's not just like, oh, this is a Sandia product and you contribute to it. We let you contribute to it because we are so nice to you, right? You need to have an equal partnership here, and that's where open governance is really important. We are actually exploring joining the Linux Foundation for that. And I'll talk a little bit about that. Todd is actually going to talk a bit about that too, I would assume. So Todd and I, Todd from Livermore, main maintainer of SPEC, we've been talking to about this kind of foundation idea for quite a long time, and it finally is coming to a more concrete point. And what we are ending up with is the current kind of working title is the High Performance Software Foundation. The whole thing is there for was intended to cover high performance software which is maintained and used at the larger community, not just at individual institutions. It's going to be inside the Linux Foundation, kind of like the Cloud Native Computing Foundation and stuff, which also has tons of different projects on it. And then there's different projects there, right? Really firm, confirmed is COCOS and SPEC. And I think Todd can talk more about that if he wants to. What there's going to be is there's some foundation board, right? And then within the COCOS technical project, we kind of going to essentially mirror the structure again, where we're going to have kind of primary projects and maybe incubation projects and stuff like that. Things which already are mature and supported widely, and things which aren't yet. There's all kinds of people we've been talking to, who hopefully gonna join this. If more people are interested, talk to Todd and I. So, what do you get out of that foundation, right? One of the things is it guarantees open governance. So what we're going to do, right, when we join as a technical project with COCOS in the Linux Foundation is we're actually going to take effectively ownership of the GitHub organization. We're going to tell them you can assert trademark on this thing. We're going to take over domains and stuff like that. What they won't do is they won't take the copyright. Right? So copyright and license stay as it's right now. Right? There's no change on that front. We hope that this will help things like organize and pay, for meetings and workshops, as well as organize and pay potentially for some shared community infrastructure. There could be things like a shared Slack channel, which might be nice if we don't lose our messages after so much time, and as well as potentially CI. So that's something more and more projects have been asking for. We're considering things like can we organize shared CI pool, right, which allows like where different institutions can contribute like CI resources on their platforms, so that we can actually test on all these different HPC type platforms. What this foundation will not generally do is it will not generally pay for people at the labs. Right? This is not what the Linux Foundation kind of at its core really does. And yeah. So timeline-wise, Spec and Cocos will probably in October actually already go in the thing as a technical project. That doesn't mean that the foundation is attached to it, so we can't like donate to it yet, but it's already the kind of open governance and stuff like that is there. And then at supercomputing, we are hoping to announce, the kind of intent to launch this thing. And then maybe by March next year, we can have that up. And I let Todd correct all the things I didn't describe correct because it's a fast-moving, changing landscape. Did I do anything egregiously wrong?
No, it's now I gotta add some more slides to my presentation. It's good.
Yeah. So within the Cocos ecosystem, as a technical project within it, we have a kind of substructure of how we want to organize ourselves. There's going to be kind of a technical oversight committee, or whatever we want to call it. That's probably going to have representatives from each organization. We want to be a bit conservative, similar to the ICC++ committee, right? So supermajority votes are necessary if there's some kind of disagreement about the direction or whatnot. Generally, I expect to just work standard, consensus-based open source development approaches. Right? But sometimes, you need to have a formal way of resolving issues if there are issues. So primary projects, right, things like Cocos Core and Cocos kernels, the goal here is they need to work on all the ecosystem supported platforms, right? You can only be a primary project if you actually support everything the Cocos ecosystem says we want to support. They expect strong user support, stable developer base, and subject to full open governance process. Secondary projects, are kind of on where they were, right? It's the best effort to support all platforms. We're working towards strong user support, etc. And then generally, they have like smaller developer base, but it's kind of like an ask for, are there other people who want to really work on this, right? Where this idea would be useful. And then associated incubation, maybe sandbox projects, whatever we're going to call it. These things might only work on some of the platforms or even just one platform, but it's, we're saying, I want to be part of this, right? I want to develop in this direction. I'm looking for other people to collaborate around this idea on, and please join forces, Yeah. So I'm hoping what you get away from this is that the Cocos team is really, really committed to collaborative community development, right? We want to do this. We want to make this a larger thing, and not just, larger within DOE, but beyond even DOE. We actively seek more contributors. We are willing to invest in productive collaborations, like the fact that Damien and I came out for 2 weeks here in order to get the CA collaboration started. We are joining the Linux Foundation to create this level playing field for partnerships with the Cocos ecosystem. But for those people who have any influence over funding, right? Making something open source, building a community, right, is not a replacement for sustained funding, right? We can't just say, oh, this is going to be a community project, now we don't need to fund this anymore, right? This is not how this will work, right? We still need the money. Thank you.
Thank you.
So, you guys have been successful enough that there are more and more Fortran projects that are wholesale changing over to C++ so that they could make use of your tool. Have you thought about extending your ecosystem to make tools that might do some part of translation of Fortran to C++ in an automated way?
There have been people who thought about that, right? The problem is that I don't really have people who have real experience in that, right? on my side. I think it's actually a good idea. I actually believe that translating Fortran code to Cocos code is more straightforward than general, right? Because there's all kinds of stuff we already have which at least map syntactically pretty close to where Fortran is, like our multidimensional arrays, for example, right? There's a one-to-one translation. Your index calculation, actually it's exactly the same thing, right? That said, there is no active project for that. I mean, it might be something somebody could propose, right? And I think it's not a bad idea to do that.
So you're also aware of the solution that we generated for ourselves to unify our codes. And what I'm finding in chatting with collaborators who have Fortran codes is they're seeing that as an intermediate step towards.
You mean the YAML?
No. The based on macros. You don't remember. We talk often.
Oh yeah. Sorry.
Yeah, no, that's okay. But yes, so this is what a lot of the new collaborators that people with same problem as me are looking at and thinking of as an intermediate step towards transition to C++.
Yeah.
But there are others.
It's a hard problem, right?
So I have this model that a new machine comes in, say Fujatu, say Aurora, and you compile your code and you get X level of performance. But then, with working diligently, understanding the hardware, using performance counters, using tools like HPC Toolkit and TAL, and on, you're able to map your library, learn more about this particular architecture, and get better performance. I'm wondering, is that the case for Cocos? And if so, how much time does it take for you to go through this process for a new machine? And Fugaku and Aurora would be especially interesting if you have those things off the top of your head.
So the time to, there's a multifaceted answer to that, right? Pieces of this we can do within Cocos, right? There's certain kind of optimizations and heuristics we can figure out, to do things. Other pieces you can only do at the kind of application algorithm level, right? I mean, Cocos doesn't provide you with all the algorithms, right? Now, how long does this take? It depends, right? If you have to write a completely new programming model and you have to debug the vendor toolchain because it's, somewhat suboptimal at the beginning, it takes years, right? I mean, Circle is still breaking us every single release, right? Every single release they come out, it breaks our unit test in some way. After that, it can be, depending on the application, it's a matter of like months. Cocos has some tuning things, you can choose things like team sizes, you choose like how you tile your problem or whatever, that kind of stuff. There's other things where it's relatively straightforward, Cocos, and the way people have to write Cocos code, right, it encourages you to write stuff in a way that it's imminently more mappable to, a wider array of things, right? You're very discouraged from writing fairly kind of a hardware-specific code, and that generally leads to better performance all around, like from the get-go. But yeah, it takes time, and it really, really depends, right?
Okay. I think we can thank again the speaker. Next talk is about Eduardi and.
Thank you. So I'm Fabien Valligand, and I am with Eduardi, and we will be talking to you about the SINSA project that is just started at CE. It's a good continuation of what Christian just talked about, because as you will see, we will be talking a lot about Cocos. And as Christian has already spoiled, we are joining this movement. To give you a context, but you already know probably much more, at CA we are using intensively HPC for numerical twins, climate modeling, nuclear, etc., etc. We are using it in all directions. And exascale is is coming. So soon enough, we will have supercomputers coming in Europe, which will be hosted at CEA TGCC. And starting from this, there will be a big need for us to develop applications to really harness the power of exascale. On top of this, we are using more and more intensively GPUs. As you can see on the diagram, 20 years ago, there was not so much use of GPUs, and now we're almost at 64%. So it's mandatory for us to have a great use of GPUs. GPUs deliver raw power, but we need middleware, we need software catalysts to be able to benefit from it. So in order to have performance kept portability. In the US, they have already understood it. That's what the exascale computing project. They have created Cocos, which has an open source strategy, but now you should be pretty much aware of all of the details of Cocos. In Europe, and in particular in France, we have research, but we don't have technology yet. So there's a learning for a sovereign solution to have our own roadmap to adapt to our specific needs, our own software, our own hardware, and probably our own software on top of it. Especially the software which is bleeding edge today will become regional 10 years later, and in our personal computers 10 years after. So what the project consists of? Sorry for the French in the figure because I couldn't know it. So there are lots of libraries already existing, Cocos in particular, and we want to create this middleware, this catalyst, this sovereign catalyst to optimize GPU calcul, in particular for exascale. So, and to demonstrate the value of this middleware, we will very pragmatically start with a few use cases inside of CEA. And Edouard will be talking much deeper about those use cases. So we want to build this catalyst, we want to adapt the different use cases, and we want to communicate and train to Sexa and Cocos inside CEA and outside. This is a very important aspect of this project. Very briefly, we do not want to reinvent the wheel. We want to adopt and adapt Cocos. Cocos is a powerful platform. Christian already mentioned many technological details about this. It's mature, it's free, it's open source. It has an architecture for performance portability. It's ready for future machine. It has also strong links with the C++ ecosystem, so it also enables us to benefit from this. There are, as I already mentioned, required adaptation for the European hardware that we will soon know about, for CEA and European applications, specificities that we want to take into account, adequation to distributed memory, heterogeneous architecture support, and on software side, interface with third-party data processing tools, PyTorch, TensorFlow, linear algebra, and ease the deployment on computers. Briefly, what will be the ecosystem around Sexa, the upstream, as you probably have understood it now, intensively getting fed with Cocos. We want to work hand in hand with the Cocos development team, and this is the reason why Christian and Damien were last week at the kickoff of the project, and they were here to do a 3-day training with our team. So we want to create strong connections. We also want to have HPC, CA libraries like MPC, DDC, Arcan, integration and communication. The partners, so we want to give back as much as possible to Cocos. We want to contribute very strategically, pragmatically with them, and with hopefully also a C++ committee, maybe, to normalize, to hopefully improve the durability of our work. Other connections are obviously the Jules Verne project, the exascale in France. We have strong connection with GenC, TGCC, and Impex, which is a French project to create a software ecosystem around the existing machine. Especially, we will soon enough be aware about the architecture choices, so it's important to take those into account. And hopefully by 2025 we want to have Sexar being production ready. Downstream there will be sort of the different use cases that Edouard will be talking about just after. We want to have co-design teams, people who are specialized into creating the software using HPC, and our team being specialized into creating the middleware on top, of course. And we want to have trainings, hackathons, to share as much as possible the experience, to have a great community that Edouard will be aiming to build as much as possible with the rest of us. And we want to have friends, Europe, worldwide visibility with this project. The follow-up will be obviously GPUs are being used more and more intensively for general computing, so it will be at the heart of the stack, and we want to have a unique competitive edge for the years to come with this project. Just to give you a few details about the project and its execution, we have a funding for 4 permanent people, 6 temporary people for 2 years, and we want to have organic growth. We will have an extended team with in-kind resources, people from the CEA, which will be not funded by this project, but which will benefit from having their code being refactored and optimized using Cocos, using Sexar. And the rest of the community is very important. I already mentioned it. We want to have a network federation. We want to co-design as much as possible. We don't want to have a backlog which is coming out of nowhere. We want to make it with Cocos team. We want to make it with people who are creating those applications in CA, in France, in Europe. We will have an agile execution, so you can find out the concepts which are very regularly mentioned with the product owner, which is centralizing all the different needs and grooming backlogs, etc., and different teams which will be executing against this backlog. The 3 lanes of work will be creating this Sexar library and give back as much as possible to the Cocos ecosystem. We want to have co-design with them. We want to have co-design with people who are developing use cases. We will be starting them sequentially to remove as much as possible the risk and to create this communication during the project. We have already identified epics for our backlog. I will not go through each of these. We still need to refine them as well with the Cocos team. So Daniel and Christian, you will be working with us on that, hopefully. Thank you very much. And now Edouard will be talking more about the use cases that will first be supporting this Sexar middleware.
Hello everyone. So now I will present the use cases that are embedded within this Sexar project. So it's use cases, but they are all based on a real production application of CA, and so they are all very important for the CA program. So the first use case is Gisela code. So it's a code that is used in the framework of the ITER project. So it deals with plasma turbulence using a gyrokinetic method, and it's a key tool within the ITER simulation tool chain, which has various code, some from, I would say, easy code to be run fast during experiment, and other mostly first principle code to understand plasma turbulence, which is key for reaching fusion. So Gisela is one of these first principle physics code and a key tool to understand fusion. So it's a highly parallelized code running already at petascale. It's a code written in Fortran with a hybrid MPI OpenMP parallelization. It's really a highly scalable code. I think it ran on the full Ukraine configuration in Yulish with almost 2 million cores, and it's very efficient, and it's very much used. It's about 150 million core hours per year that are used with Gisela for a scientific application. So Gisela was ported to many of the current high-end architecture. So Fugaku, Adastra, which is a new computer just bought at one of the French computing center, and CEHF, which is a new computer at the CA Computing Center. So we had a good performance, good scalability on all these architecture, but this was not possible without rewriting and duplicating most of the kernel, which means it was a huge work which has to be done with HPC expert, and each time we change architecture we had to rewrite a lot of code, and it was extremely tedious and time consuming, and we believe we cannot go on like this for a long time. So the roadmap for Gisela, so it's a legacy code, it's a 20 years old code, so we have a lot of know-how and expertise in this code. We have a unique code, but it's very difficult to optimize for all architecture, and as I said, we need a lot of code rewriting. And we also want to enhance the physics, so having a new meshing technique, which we need anyway to rewrite many kernel, and train the X-point geometry, which is a particular point within the tokamak, which also need to modify deeply the code. So with the team it was decided that it was simpler to fully rewrite the code, and I wouldn't say throw away because we have all the experience from the previous code, but rewrite the code in modern C++, so using a new technique and better, I would say, software engineering techniques. So the first proof of concept was done with a small code in C++ and a 2D code. Based on DDC, and DDC is this meshing library which is itself based on Cocos, and so it was a small code with one dimension in space, one dimension in velocity, but it was a very good proof of concept, and the team has adopted the principle for the next version of Gisela. And so now we are in the way of writing Gisela X, which will be the exascale code. So it will be this time the full 5D code in C++, and of course we hope it will scale on all the exascale architecture. So it will be based on MPI for multi-node parallelism, and Cocos from intranode parallelism, and also we have been working, I won't talk much, but PDI for the in-situ analytics and I/O, which is also a key issue for large simulation. So we are now in the process of slowly building up and adding all the physical modules in this new code, and we hope to have a first, I would say, physics results in maybe a year or so. And then we will be slowly adding all the physics. So that's on its way, with funding from both SEXA project and also other source of funding from Europe and Eurofusion, EuroHPC, and other projects. The next code is Trust and Trio CFD. So it's a CFD platform and application. So Trust did with fluid mechanics, incompressible, study incompressible, eventually with multi-fluid and with front tracking, with a lot of application for reactor physics, mixing, study of fuel cells. It's also open source, so you can check it out if you would like. And Trust itself is a large platform where many CA key applications are built upon. So for many for reactor physics and a bit wider. So it's really an important numerical tool for CA. And so for now, we are working just on the Trust Trio CFD application, but once that's done, we will be able to extend that to all the other applications built on Trust. So there is already quite a lot of experience in GPU porting in this team. So mainly through the usage of library for linear algebra, which is a very consuming part of the code, and they have been slowly implementing and trying to port part of their code to GPU to gain in computing power. So the approach is a bit different from Gisela. So the idea is more classical to analyze the code, see where you have highly intensive computing kernel, and then push them to GPU. So for linear algebra, that was using library, and then iterate like this to try to port the code to GPU. So they had very good result. For example, porting linear algebra with the AMGX solver to GPU. So you can see that the linear algebra part had almost 9 times speed up on GPU using this library, but of course you keep the rest of the code on CPU, and it still takes a lot of time. So then you go back again, see what is the next most computing demanding kernel, and then you try to port it to GPU, and you iterate like that. And so with the analysis, they believe that slowly building up and introducing COCOS within the code would allow to do this in a smooth and nice way. Also, they have to change their test case, so it's not a surprise for you, I guess, but with GPU you need to go big, so you need to fit the GPU, and so basically the GPU efficiency rises with the size of the problem, so you have to treat and to have a large test case to be efficient on GPU. And also, I guess it's the case for many code, with a simple roofline analysis, you realize that the code is memory bound. So you can have your performance is limited by memory access. So they have reached 15% of peak performance, which I believe is still not that bad. And so now they're trying to modify the code to recompute some data instead of storing them, to have, I would say, a higher compute intensity, and trying to leverage this memory bandwidth limitation. And so for this routine, so Trust, it's also on its way. They're slowly porting kernels to GPU and introducing COCOS in most of them. So the last application is TrickLab. So it's an application dedicated to turbulent mixing. So it touches a lot of topics at CA for astrophysics, geophysics, inertial confinement fusion, and also some defense application. So it's a very complex problem. It's intrinsically 3D and multi-scale, both in time and space. So, for example, you have here an example of a shock wave through, I would say, an interface with helium and air, and you can see the mixing developing. So it's highly compressible, and here the code is on a structured Cartesian mesh with shock capturing technique. And so it's highly complex, multi-scale, so you really need to do large exascale run to study many physically relevant problems. So the code is in C++. They say it's not really modern. It's 100,000 lines of code, so still a big chunk, not huge, but significant. You have API for domain decomposition, and a modular design, so one module, one numerical scheme, which makes it easy to port it piece by piece, and a few dependents on outside the library. So for TrickLab, they have decided to port the code to GPU using COCOS by physical models. So they roughly impact 10% of the line of code. So they choose the M5 numerical scheme, a few key solvers, and they will first implement this, so they can run some physics using COCOS, and then slowly they will be implementing other scheme using COCOS. So the conclusion of this first work on our demonstration code is that COCOS is an efficient way to port application to GPU. You have a very good performance portability, which is one of the key reasons to use COCOS. We hope to leverage on the strength of the COCOS community, so both within CA by having many people using COCOS, and of course outside CA in France and wider, as was presented before. We are organizing ourselves to provide feedback to the COCOS team and to have exchange. And another key aspect is long-term sustainability of the code, of course. just stole this slide from Christian's presentation that happened just before. So we would very much like to contribute to this virtuous circle, and I think it's a key aspect. So I would say in the computer science community is very active, it's very dynamic. There's a lot of tools being developed, which is good, but from the user perspective, you really need to build trust and to have a tool which lasts and will have a large user community. That's the only way you can really have confidence in the future, build trust and build experience. So really having people gathering around a few key tools, we believe it's a key aspect for long-term sustainability and performance of a key HPC application. So as a conclusion, we hope with EXA to have a sovereign tool to harness exascale computer, which is of course key for CA. There's a large variety of applications across CA. So across CA for us is very important because CA is a large organization. So I presented the application from all various large CA divisions, which means there is a lot of momentum inside CA. Many people are concerned, and so strong support from the CA head. We are trying to build a community both around key application and about COCOS, so gathering people from application and people from computer science, and everybody is strongly motivated. And this collaboration between application people and computer scientists is key. As was mentioned before, we hope to have a strong collaboration with the COCOS team. There's large impact on CA program and on all the work we do. We target performance, portability, and code sustainability, as most of you, I guess, and it's really a key challenge for legacy application. And for that, building a strong community is really instrumental, because that makes the tools better, that makes the tool last for a long time, and that allows to share experience, to talk with colleagues. So it's really key to have this community. And another key aspect is to keep application scientists on board. So C++ in some community, people are a bit reluctant to use that, so we need to help people to do that and to keep people doing the science with the code together with the people developing the code. Thank you.
Thank you very much. So we have time for questions. So I have one. Could you explain a little bit in more detail what kind of, take some example, what kind of features you don't find in COCOS and to be developed inside EXA and benefit to COCOS and specifically for either CA application or European architecture or so? Just one or two examples.
Well, that's work which is on its way. I think we have that's really that's the backlog we are now trying to set up. So we are talking with the team to see. So it's a long process. We need to explain to the team what's inside COCOS, and then they need to identify what's missing. So the first step was to develop DDC. So it's a kind of a mesh library which goes above COCOS and which was needed for Gisela and for many other applications, where you have a more flexible way to manipulate the unstructured grid and with cell-centered or fair-centered variables, so a bit of an extension of COCOS. And so we are slowly finding things with holes in COCOS which we would like, where we would like to fill the gap. Then maybe we will contribute also to making COCOS more efficient for some features that are key for us. And then the big thing is eventually develop or co-develop a new backend. For example, if there are European hardware coming out, then we would need, for example, a specific ARM architecture, then to adapt the backend already present in COCOS to be more efficient and more adapted to a European hardware.
So you mentioned on your slides the interaction with the C++.
Yeah.
Will you also be developing to evaluate those parts of the C++ standard that are ready for parallel computing?
Yeah, so that's developing. So as was mentioned in the previous talk, Cocos is working hard to push things into C++. We believe it's a great idea because it really makes things sustainable and give you a long-term perspective. So we hope to contribute to that. For now, we are not, but we are discussing. So Christian and Damien were at CA last week and we are talking with them, and we hope to get involved in this process to push feature into C++. And it's a long time, I mean, it takes a long time to push things there. So first work into Cocos where you're more free to make development, and then try to push the good idea within C++. Yeah, I think it's a good way to proceed.
Okay, thank you very much. Hi, Christoph Hoinger from Intel about preparing an application for Aurora and how to develop a scientific application to the desktop computer. So the application is the main development of the application.
Okay, so my name is Christoph Bauinger. I'm an application engineer at Intel, and today I'm going to show you what we did with Big DFT to prepare it for Aurora. And what I'm showing you is work I did together with Luigi Genovese, who's over there, and his team. Alright, so we have some notices and disclaimers here, some legal stuff. Why are we even talking about that? Well, this is the motivation. Aurora is the new exaflop system, or exascale system at Argonne National Lab. And I'm not going to bore you with any details about this machine. The interesting part for me as an application engineer is that it has 2 exaflop of peak performance. And for me as an Intel application engineer, it's interesting that it comes with Intel data center GPUs. And even more interesting is that we cannot use CUDA code on these Intel GPUs, which means we have to put some effort in to make our applications run on this machine. Alright, so one slide about the data center GPUs in there. So you may have heard of them under the name PVC or Ponte Vecchio, so that was the code name. Now it's called Intel Data Center GPU Max 1550. So I'm going to just name it PVC in the rest of the presentation. And for me as an application engineer, there's one really important thing. When we run something on this, we need to consider that this is not one big monolithic device, but it actually consists of 2 stacks. So we see it here in this picture on the right-hand side. Two stacks on top of each other, which are connected with an interconnect, an NDFI. And the PCI Express connection is just in the first stack on the top. And that means that typically when we run something on this device, we use 2 MPI racks. And when I talk later on in my presentation about half a PVC, I mean that around 1 MPI rank on 1 stack. What's also interesting, this will come up later in the presentation, the thermal design power is 600 watt of this piece of hardware. Right, a little bit about the XE core, so that's the what drives this machine. And, one XE core, that's where the L1 cache lives, that's where the instruction cache lives, that's where the vector engines and the matrix engines, the X and X live. So that's what is a tensor core on NVIDIA hardware. And in the vector engines, that's what was called execution unit before, that's where the register file lives. So, okay, that was the hardware. Now, how do we program PVC? You can use OpenCL, you can use OpenMP, you cannot use CUDA, and you can use SQL. So SQL is an open standard developed by the Columbus Group, which was initially released in 2014. And it enables to write single source C++ code for heterogeneous and offload processors. Okay, what does it mean? Well, we see a little example code on the right-hand side, and we can see that we have a cyclic queue here, object here, and we can submit jobs with this parallel 4 function in line 11 to this queue. And this parallel 4 function takes 2 input parameters, the ND range, which is the grid and block size in CUDA, for those who are familiar with CUDA. And the second parameter is the lambda function, and that's the kernel code that's actually run on the device. And this cycle standard was implemented by several different groups. For example, Compute CPP from CodePlace, one of the implementations, or HipCycle, or what we are using here, the One API DPC++ compiler from Intel. All right, so that's technical background. We have seen the hardware we are aiming for. We have seen the software we are using. Now, let's talk a little bit about the code. So big DFD, the code we want to enable for Aurora, is in implementation of Cohen-Chang density function theory. I have no idea what that means. If you have any questions about DFD, go to YouTube, please. And what's more interesting for me is that it's a Fortran code with some parts of C++, OpenCL, and CUDA. And this code has been CUDA enabled, or one path of this code, since 2009. And there are also some OpenCL parts for the offload. And this CUDA implementation was shown to perform very well up to a couple of thousand of NVIDIA nodes. So there are publications I cited below showing that this implementation is really working very well. So what is it doing? We need to evaluate what is called the Fock operator. So that's basically some integral over some quantities divided by the distance times another quantity. Whatever, so for the math savvy, that's what we do. For everyone else, just forget about this slide. What is really interesting here is the second part. So this is just a multiplication, the first part. The second part is solving the Poisson equation. That is the performance critical part, which we are looking at. And the third point is just, again, a multiplication, so we can forget about that as well. To solve this Poisson equation, the algorithm uses multiplication in frequency domain. So we use an FFT to go into the frequency domain. Then we multiply with the kernel, with the green function. And then we use the inverse Fourier transform, plus Fourier transform, to go back to the original values. And there's one problem. If we do not have periodic boundary conditions when solving this Poisson equation, then we need to zero pad. So we need to add zeros. So this is indicated in 2D by this figure. So the original domain would be the red grid, and the zero padding would be everything else. And we see, okay, that 3/4 of our memory would be filled with zeros if we do that explicitly. To avoid that, the algorithm uses batched 1D FFTs. So first it does the FFTs, one-dimensional FFTs in the x direction, and pads with zeros if necessary. Then it pads in the y direction and does 1D FFTs there, and then it goes to the z dimension. All right, so this is the algorithm. You see, if our boundary condition in x is free or actually non-periodic, we need to zero pad, and then we do 1D FFTs in the x direction. Then we do the same for y, and we may need to transpose the data, which means we want to have the elements in y direction to be contiguous in memory. So we need to shuffle the data. Then we do 1D FFTs and the same in z direction. Then we have a multiplication in line 13, and then we do the inverse. Okay, so this is implemented. This is the CUDA code. That's what the CUDA code does. This is what we need to bring to SQL. And since this CUDA code works really well, our approach was, well, let's just use it and copy it. And the way to do that is by using the compatibility tool. So Intel developed a tool where you can plug in CUDA code and it spits out SQL code, and that's what we used. An example is on the right-hand side. It's one of the GPU kernels on the top in CUDA and on the bottom in SQL. And it's basically the same code. The only difference is that in SQL we have the information about the grid as an explicit parameter here, which is given implicitly. The translation also inserts one MKL FFT calls instead of two FFT calls for these 1D FFTs. And after we did that and do some manual stuff, so about 95% of the code we're actually working after doing this, and after fixing the other 5%, we got really good results on PVC. So we were done, basically, or I thought we were done. And then I went to the CPU and ran it there, the SQL code, and it didn't perform at all. Not at all, but significantly worse than the original CPU version. And that was surprising, because one would think, hey, if we use 1MPL, this is a highly optimized library, why is this not better than the homebrewed FFT? Sorry, Luigi. But so I analyzed this, and we saw that on the CPU, the SQL code has problems with the zero padding and the transposition of the data. Since every time we zero pad, we need to move the data around, so one read, one write, and every time we transpose the data, we have one read, one write, at least. And that hurt us. That was actually more expensive on the CPU than the actual FFTs. So, here indicated in red. And to get rid of those, we used a different FFT library, which is called the double-patched FFT library. It's an open source library. There's the GitHub repository for this library. And what this can do is it can use zero padding on the fly with callbacks. So you can tell the FFT library what or where to take data from, and under certain conditions you can say, hey, just take a zero, and we don't have to insert it explicitly. And we can also avoid the data transpositions with this library due to the double batching feature in BBFFT. We then also optimized a little bit here the convolution, so the multiplication with the kernel, and overall this meant that we halved the memory requirements for the SQL version using this library, and we more than halved the computing time on the CPU. And at this point, so this is implemented, this is pushed to the official repository. At this point, we have a very good implementation, SQL implementation on PVC and on the CPU. And I'm going to show a bunch of results, benchmarks in what follows, and I want to point out that there are some comparisons to NVIDIA hardware, and those are not fair. So I want to understand everyone that the NVIDIA system is using older processors, has no NVLink, and that's not really a fair comparison. So not anyone goes and thinks, hey, he's comparing apples and bananas and saying PVC is better. So that's not my goal. What is also important to note, so if you remember at the beginning of my presentation, I told you that PVC has a thermal design power of 600 watt. In this test system, they are actually limited to 450 watt. So it's a reduced pressure power factor. Okay, those are some results. So from the left, we have a very large, or a large, probably not very large, with few orbitals. And we ran this in the blue curve on half a PVC, 1 PVC, 2 PVC, 4 PVC. So each node has 4 PVCs, and then 2 nodes, 4 nodes, and 8 nodes. So who wants to tell me what's wrong with that plot, the blue curve? No one? Really? A room full of benchmark people and no one can tell me what's wrong with that? Yes. Okay. So. Yeah. Yeah. So there is one really odd point here, I would say, this one. I mean, this one we can explain, the problem just gets small enough that the overhead from the communication hurts us here. But this one is a really odd point. And there are two reasons for that. First, the power cap. Like limiting the device to 450 watt hurts us when we go from half a device to the full device. So the performance is limited in that case. And, so that's the first point. The second point is that the benchmark, this FOC mini we were using to evaluate the performance, does not have, or the number of operations required scale with the number of API ranks. And so it's not a great test case, but it's representative for what's happening in big DFT. So when we go from 1 to 2 ranks, we actually increase the number of required operations by 50%. And when we go to 4 ranks, we reduce them by 25% and so forth. So the superlinear scaling after one full PVC is also due to a reduction in the number of hops. Okay, but what we can see here is two very important things. First, the GPU implementation scales. So it's not getting slower. That's not perfect, but it's something. We also see that the GPU implementation is significantly faster than the CPU implementation. And what we can further see is that the SQL implementation on the CPU is about a factor 2 faster than the original CPU implementation. So due to introducing this double batch, the FFT library, we significantly outperform now the original CPU plus OpenMP, so Fortran plus OpenMP implementation. We have here in the middle a different test case, a smaller test case, where we also compare against the CUDA implementation on A100 GPUs. And we see, okay, not too far off. There's no clear winner. Again, I want to point out that comparison is not entirely fair, since the CPU is different, although the CPU is not really important in this test case.
Can I ask something?
Of course.
Are you just telling me when you're comparing a single A100 to one 52 teraflop, how many terabytes a second?
No, I'm
total
comparing,
device?
Yeah, like one PVC against one A100.
So one PVC with 2 GPUs essentially in it, right?
With 2 tiles, yeah. One PVC GPU.
So you're comparing a 7 or 9 teraflop thing to a 52 teraflop thing?
Yes.
Okay.
Yes. So, as I said, the comparison is not fair. But there is not really a great way to compare these things if you just look at number of devices. Okay, and then we see again, even for the small test case, that the SQL CPU version is significantly faster than the original CPU version. Finally, I'm doing the same for a large test case, and here we see similar behavior. The scaling is better on PVC. The speed up of the SQL CPU version versus the OpenMP, Fortran OpenMP version is still a factor 2 approximately.
Excuse me?
Yeah.
What is the reason for this speed up? Is it because all these operations seem to be fairly low arithmetic density? So would it be memory bound? Is it just the memory bandwidth that explains the speed up? Yeah. And
so in this case, we have one A100 against one full PVC, but in the full PVC delivers more memory bandwidth in this case.
Yes, it's probably the only reason why you're getting the curves.
Yeah.
The curves. And is it running on multiple nodes? All this?
Yes. So we have here 1 node, 2 nodes, 4 nodes, 8 nodes.
And how did you? Was there a problem with the distributed domain transposers? How did you deal with that? Because it's often a problem with multi-scale, multiple dimension FFTs on multiple nodes.
Okay.
So you get all-to-all communication, which is
each FFT is on a single GPU. The partition happens further in the process. So the FFTs are not distributed.
They aren't distributed, and the domain transposers, are they
Happens
distributed?
at a different point in the code, outside of the FFTs.
Okay, so that's why it's not that impacted.
There's no MPI calls within the FFTs.
Okay.
All right. So we took this, went to the full code. Oh, sorry. First of all, I measured memory bandwidth to see what happens. These two examples. So the first example on the left-hand side is a large example, which takes about 60 gigabytes of memory. And we see that most of the traffic is in HBM memory. So we achieve close to 800 gigabytes per second on a single tile of PVC, which is not that bad. So that's the average over the whole application, everything from start to end. PVC has on paper a memory bandwidth of 1.6 terabyte per second on one tile. Realistically, you get for real world applications up to 1.1 terabyte per second. So we have 800 gigabyte out of 1.1 terabyte per second. This tells us there's still a little bit of room for further improvements. But we're not horrible. And the second test case, that one is small enough to fit in cache. And we see that with the L3 traffic. All right, so when we look at the full app, we see similar behavior. So we ran the full app, not this little mini app from before, and the results hold. The only thing that is a little bit weird here is the comparison between SQL and CUDA, since before in the mini app they showed the same performance. And the reason here is the different CPU. So if we use a different CPU for the SQL part, we see the same performance here. All right. Now let's talk a little bit about performance portability. So we saw that the SQL implementation works very well on the CPU and on Intel GPUs. Can we extend that to different backends? In theory, SQL can do it. So there is a backend for AMD GPUs, for NVIDIA GPUs, for FPGAs, if you want to do that. And that's the goal, to make it work on all of these different architectures. The problem is it does not yet work. The reason is the introduction of this double-batched FFT library, which is not meant to be used on AMD and NVIDIA GPUs. So our solution is going back to MKL. And MKL, there's an open source version or an open source interface, which is also called one MKL, which has support for all of these backends. That is still work in progress, so that is the next step for us. Okay, let me summarize real quick what we saw. So we have shown that the porting CUDA to SQL, even in big applications and big codes like big DFT, is not really a big deal. We have tools for that, and CUDA and SQL are close enough that it's not a problem. You've also shown that SQL plus PVC performs and scales reasonably well, which indicates readiness for Aurora. And then we have shown that SQL on the CPU is a good alternative to the existing Fortran and OpenMP implementation. In the future, what the next steps for us are, we want to work on AMD and NVIDIA support, and we want to run large simulations on Aurora. So we really want to see how large we can go. All right, that's it. Thank you.
Thanks for the talk. I have two quick questions here. One is, you mentioned that per PVC node you have 128 HBM memory. So if you run 2 ranks, that is per MPI ranks, you can see 64. Is that correct?
Yes.
These are HBM3 or 2E?
That is a good question. I do not know the hardware.
Okay, that's fine. The second question is, if I recall the number correct, one PVC, you have this same double precision, well, 32 as well. But altogether, you have 63,000 PVC nodes. If my math is correct, you have pretty much like over 3 exaflops in your system, the raw power wise. So the estimate of just 2, I think the advertisement is bigger than 2 exaflops seems rather conservative. Can you comment on that, or?
No, I didn't do the numbers for the machines.
Okay.
Yeah.
If you multiply that 60, yeah.
But no, I don't know who put that together. Sorry.
So if I understood properly, you introduced a double batch algorithm for CPU, right?
Mm-hmm.
Did you look at performance on the initial port to GPU? Was it comparable to what you could achieve with what you could do with SQL?
In that case, the transpose and the zero padding were not really a bottleneck on the GPU due to the higher memory bandwidth we have available. So the performance in that case was pretty similar and was only dependent on the problem size. So some FFTs were more performant on MPL, some were more performant on the FFT.
So do you draw the conclusion that we need performance portable math libraries? Essentially?
Well, yeah. Like 1MPL in theory solves that problem. Like not Intel 1MPL, but 1MPL. I don't know who came up with that naming. 1MPL is the open source interface. And that, in theory, solves the problem, but some functions are still not implemented.
Thank you for the talk. Any comment on contributing to the C++ standard from SQL in terms of this will also feed into C++?
Yes. So the idea is that I talked to one of our SQL guys a while back about this, and the basic idea is we have the SQL standard. Intel has extensions to the SQL standard, which is the newest stuff. Then it moves back to the SQL standard, and slowly the SQL standard merges into standard C++. That's the goal. How far and how fast this goes, I don't know. I know that there was a proposal for 23 about parallelization and offloading that was completely overhauled by Intel engineers. But that is information from 2 years ago. I don't know how far they are again with that. So maybe the Cocos guys know more about that since they're more involved.
Yeah, and the SQL guys are not really.
Okay.
So most of the parallelism stuff. Do you know of any SQL person who is on the standard receivers?
I think some Intel person, but I'm not sure if they're still
but
within
it's been mostly driven by other people.
Yeah.
And there has been relatively little engagement from SQL persons directly on that, as far as I can tell.
Okay, and I would need to check which person is involved in that. Or
there's somebody from AMD who used to be on the SQL stuff, who's also in the committee and who does a bit of that. And then some of the Intel folks are there. But I don't think they have been super instrumental in designing the senders receivers thing, which does not have any kind of similarity to the SQL interface at all.
Yeah.
There's, I don't know. Right now.
Thank you. Interesting talk. I think you mentioned some detail about interface stuff. So for the multi-node, what kind of internet do you use, and so how do you such kind of GPU direct thing, such kind of thing? So could you tell me some detail of that stuff?
So GPU direct on Intel GPUs. That's what you're asking, right?
Yeah. So in your case, you are using or not AMD stuff or not?
No, we use GPU direct. It's implemented in Intel MPI since 21.8, I think, reliably.
And which kind of interconnect for the MATIN?
The machines have a the NVIDIA machines have a Mellanox interconnect, and the PVC machines have 2 NICs HDR interconnect. Yeah, they are different. Like, don't take these numbers, these comparisons of NVIDIA versus PVC nodes one-to-one. They are just to show, hey, we are in the same ballpark. We are playing the same game. We are not somewhere else completely. That's all we really can draw from that. And even that is already a questionable conclusion. It's also important to note I used in all test cases Intel MPI, which has a hidden support for NVIDIA GPU Direct on Mellanox fabric, but it may not be optimized perfectly.
Okay, we can thank the speaker again. It closed the session this morning, so now we have lunch exactly at the same place as yesterday on the bed flavor. And so please come back at 1